Hello everyone, and thank you for joining us today. My name is Heongwon, but you can also call me Chris. I'm honored to be the first presenter for the Rilem Conceivable Peer-to-Peer webinar. I'm currently based in Seoul, South Korea, where I earned my PhD from the Department of Architectural Engineering at Hanyang University. And my academic and research background is in construction materials with a particular focus on the cementitious systems. And during my PhD, I explore how the nanoscale pore structures in cement-based materials influence the fire-resistant performance. So let me begin my presentation. The title of my presentation is Fire-Resistant Mechanisms in Low-Lying Calcium Silicate Cement as a Carbonatable Binder, a synchrotron X-ray nanoimaging approach to nanoscale pore structure analysis. So here is my outlines of today's presentation. First, I will explain the research background and objectives. Next, I will introduce the experimental and analytical methods. And then we'll move into the core of the study with the result and discussion. Finally, I will summarize the key findings and the conclusions. Research background. Our research begins by addressing the urgent global goal of carbon neutrality by 2050. This stems from the decades of climate action, starting with the UNFCCC in 1992, followed by the key milestones like the Kyoto Protocol and the Paris Agreement, and recent national updates in 2021 and 2023. Countries have set 2030 emission reduction targets, raising the essential question: how much, until when, and how? To answer this, the carbon neutral roadmaps have been developed across 5 major sectors, and among the sectors, the industrial contributors, the cement industry stands out due to the large amount of CO2 footprint. In the cement industry, the carbon emissions are a major concern. Actually, cement production accounts for about 27% of industrial CO2 emissions among OECD countries. And cement manufacturing inherently produces large emissions, especially during clinker productions, and which involve high temperature sintering of raw materials. And further emissions occur during cement blending, aggregate processing, and also concrete mixing. To tackle carbon emissions in the cement industry, the major organizations like PCA and SAMRO and GCCA have proposed strategic roadmaps. PCA promotes the value chain approach in targeting emissions through clinker, cement, concrete, and construction. Their roadmap includes the short-term actions and also the long-term tech innovations. And SAMRO introduced the 5C strategy, focusing on 5-stage clinker, cement, concrete construction (CCUS), which specific reduction goals and methods such as renewable energy use and expanded CCUS adoption. And GCCA aims for net zero by 2050 by reducing clinker use, improving mix design, enhancing energy efficiency, and accelerating CCUS. Together, these frameworks provide practical and measurable steps toward decarbonizing the cement sector globally. And cement production emits about 667 kilogram per ton and CO2. And SAMRO's 5C strategy highlights CCUS as key to cutting emissions by 42%. And CCUS involves capturing CO2 and either converting it into useful products or storing it underground. To realize this, major R&D force, technology validation, and standardization evaluation methods are required. And this slide highlights the 2 key parts of CCUS: capturing CO2 and reusing it effectively. On the left, CO2 is captured from flue gas during cement production using a purification system that extracts high purity CO2. And the right, this CO2 is applied in carbonation curing, where it strengthens cement-based materials and is permanently stored in solid form, products like blocks and precast panels. And this slide illustrates various practical applications of CO2 carbon construction solutions. Examples include interlocking block, bricks and tile, paving block, and aerated block, and precast products. And two main CO2 curing methods are showcased. First, demolding and CO2 curing after primary molding through compression. And the method is suitable for producing dense, durable blocks and tiles. And second, direct CO2 curing after casting into formers, applicable for complex precast structures, enhancing rapid strength development and structural integrity. So these products not only reduce overall CO2 emission, but also enhance sustainability by permanently storing CO2 within the structural matrix. And this slide shows the hardening mechanism of calcium silicate minerals when exposed to CO2. The carbonation reaction occurs rapidly under normal atmospheric conditions, forming layered reaction products. At the reaction interface, the ions such as carbonate, calcium, and silicate diffuse inward, creating a dense interlocking matrix of calcite silicate phase and decalcified calcium silicate hydrate (CSH). The detailed microscopic at the right, this image demonstrates the mechanical interlocking of calcite crystals within the carbonated matrix. These calcite crystals with a high Young modulus substantially enhance the mechanical strength of the cementitious materials, resulting in the robust structural integrity and durability. And this slide outlined the critical parameters influence the suitability of various cementitious minerals as carbonatable binders, emphasizing synthesis temperature and activation energy and calcium contents. Minerals like C3S, beta C2S, gamma C2S, C3S2, rank 9, and CS-olastonite differ in these characteristics, affecting their carbonation reactivity and mechanical strength. Especially the OPC, ordinary Portland cement, mainly consists of C3S, promotes the rapid carbonation due to its low activation energy and also low activation energy and high calcium contents. However, it requires high synthesis temperature, resulting in a high amount of CO2 emission during production. Therefore, ongoing research targets the alternative minerals with lower synthesis temperatures and reduced emissions, offering improved sustainability without compromising the strength and the reactivity. And as shown in this slide, the low-lying calcium silicon cement CSC is considered a promising carbonatable binder due to its lower synthesis temperature compared to that of traditional OPC. The CSC consists primarily based on the minerals such as C3S2 rank 9, CS-olastonite, and also C2S. But also CSC emits less CO2 due to its lower synthesis temperature. Its reactivity is lower compared to OPC. The lower reactivity of CSC necessitates further research on how to optimally blend CSC with OPC to achieve desirable strength performance. So this slide defines the main research objective. As mentioned earlier, further investigation is required to determine the optimal blending ratio between CSC and OPC to compensate for the lower reactivity of CSC while achieving with sufficient strength. Additionally, the carbonated binder, which are primarily based on CaCO3, are expected to exhibit the high fire resistance. As you can see in this TGA spectra, compare the thermal stability of the three CaCO3 polymorph, calcite, argon, and vaterite. Despite the minor differences, all polymorphs retain over 80% of their mass, up to approximately hitting to 800 degrees Celsius. This indicates the strong potential for excellent fire resistance performance, underscoring the importance of further research into the use of these carbonatable materials for fire resistant construction applications. So we should evaluate the fire resistance of the mechanism of CSC-OPC blend cement paste. So therefore, in this study, we use OPC, ordinary portland cement, and CSC, and this slide shows the property of these two raw materials. The particle size distribution show that the OPC and CSC have similar particle size. And the pie chart revealed the phase composition by XRD analysis. The OPC is dominated by the alide C3H with significant amount of belite C3A and C4AF. On the other hand, CSC consists mainly of carbonatable phases such as C2, rankinite, and elastonite, and also C2S. And in the experimental method, this study employed a series of CSC and OPC blended paste with mixed proportion design based on preheating compression strengths. As shown in table 2, 7 different blends were prepared with varying ratio of CSC and OPC, ranging from 100% of CSC, called C10, and 100% of OPC, called O10. Now, water to binder ratio was maintained at 48%. Okay, so for sample preparation, a dry blending of CSC and OPC was first conducted for 8 minutes, and followed by the mixing with distilled water using a high-speed paste mixer. And then the cement paste was then cased into stainless steel molds of size of 5, 10 cubic millimeter size. And after demolding, the sample underwent the carbonation curing in the CO2 pressurized chamber for 168 hours under high CO2 concentration. And this slide presents the process for creating a controlled carbonation curing environment used for paste sample curing. As illustrated, the paste specimen 5, 10 cubic millimeter were placed in CO2 chamber, where they were exposed to CO2 gas for accelerated carbonation. The carbonation chamber was initially vacuumed to 0.1 bar, followed by CO2 gas injection to pressure of 1.0 bar. Throughout the curing process, the chamber temperature was maintained 30 degrees Celsius to ensure the stable reaction environment. And about heating setting, to evaluate the thermal performance of the samples, a controlled heating program was implemented. As shown in the heating curve, the target temperature was set at 4 level, 200, 400, 600, and 800 degrees Celsius. The temperature was raised at a constant rate of 10 Celsius per minute, followed by the natural cooling. And after the strengths were measured, and its target temperature were maintained for 2 hours. For the measurement of property change after heating, the micro compressive strength test was performed on the specimens, and XRD Rietveld analysis was carried out with internal standard method before and after thermal exposure. And surface observation, surface crack formation observation before and after heating was conducted using electron microscopy. Volumetric changes were measured to assess thermal expansion or shrinkage behavior. And also, nanoscale pore structures were analyzed using synchrotron X-ray nanoimaging at the Pohang light source, PLS, and specifically at the 7C X-ray nanoimaging beam line. And the maximum sample size was 200 micrometer, with a 3D resolution was up to 50 nanometer, and 3D reconstruction was carried out using an Aviso program. And through this setup, pore connectivity and pore thickness were quantitatively analyzed by processing XCT images and constructing cross-sectional 3D models of the microstructure. So this is result in discussion. The compressed strength results show that the C802 exhibits the highest strength before heating, indicating optimal blend of CSC and OPC. And after thermal exposure, C802, it means CSC and OPC are 822, also maintain superior strength up to 600 degrees Celsius, showing enhanced fire resistance. And this performance is attributed to the improved physical filling and microstructure interlocking by Vaterite microcrystals. And even under high temperature conditions, C802 retain a relatively high volume and compressive strength compared to other mixes. And you can also find this graph, which means that the change of the volume, the C802 retain their volume the most compared to the other samples, C10 and O2, even after hitting to 800 degrees Celsius, retain the volume. So this slide illustrates the surface crack observation on cement paste samples before and after heating at 600 degrees Celsius and 800 degrees Celsius. The visual analysis clearly shows that the C10, C802, and O10 do not show the significant surface cracks appeared in the samples, and even after heating and cooling cycles at these elevated temperatures. The absence of the surface cracking indicates that the high thermostability of carbonatable binder metrics, suggesting the metrics undergoes the uniform shrinkage. They shrink uniformly, so they do not make the very visible cracks. And then it's the XRD Rietveld analysis. Analysis was conducted to investigate the phase changes before and after heating. All samples C10, C802, and O10 retain their pre-heating composition up to 600 degrees Celsius. And however, at 800 degrees Celsius, the composition of CaCO3 calcite was observed, indicating thermal breakdown of carbonated phases. And especially, we should focus on the C802, the composition of C802. This is the result of the composition which analyzed by the XRD Rietveld. In C802, a stable proportion of vaterite was maintained up to 600 degrees Celsius, contributing to its enhanced fire resistance. This result suggests that the vaterite crystals improve the thermal stability by enhancing the microstructure, interlocking, and reducing phase decomposition. The key is vaterite structure in the carbonatable matrix. So we should, to understand how the presence of the vaterite enhances the fire resistance, nanoscale pore structure, the nanoscale vaterite structure should be analyzed by the nanoscale CT. So especially we focused on the skeleton-based pore analysis, and skeleton-based pore analysis was conducted to quantify the pore network connectivity. And as you can see in this A, show that the conceptual components of the skeleton, the vertices, the edges, and points. To quantify these vertices, edges, and points, we can know how the connectivity composed. So case C, you can see the low connectivity structure with the fewer connections and the low edges per vertices ratio. In contrast, the case 2, the highly connected structure with high edges vertices ratio indicating more continuous and stable pore pathways. So this structural quantification allows direct comparison of connectivity levels between different samples. And also, we conduct the coordination number analysis, which means the high coordination number means the high networking, that highly connected structure. And so CSC, the results show that the CSC blended samples like C10 and C802 show the higher connectivity compared to OPC only blended O10 samples. And notably, the C802 maintain the most stable coordination number distribution with minimal changes even after exposure to 800 degrees Celsius. And this indicates that C802 possesses the stable pore network, a thermally stable pore network contributing to its enhanced fire resistance. It did not change dramatically compared to the other samples. And also, this is the pore thickness analysis, and this also showed that the C10 showed a significant increase after hitting the 800 degrees Celsius, and O10 exhibited irregular changes with an initial increase followed by the decrease at the higher temperature. In contrast, the C802 maintained a stable pore thickness across all conditions, showing only minimal variation even after hitting to 800 degrees Celsius. This stability in C802 further confirms its superior thermal resistance and metric stability. So, X-ray nanoimaging revealed distinct differences in pore structure and connectivity depending on the presence of interlocking structures. The sample without interlocking, this A, showed the significant pore connectivity increase after thermal shrinkage. In contrast, the sample with abundant interlocking by Vetter microcrystal, BND, exhibit the restricted shrinkage and improved the thermal stability. In particular, C802 displayed the dense interlocking and minimal pore expansion, confirming its superior fire resistance, and this is attributed to the enhanced physical filling and microstructural reinforcement from the Vetterite formation under heating condition. So this is conclusion. The CSC to OPC ratio 8 to 2 demonstrate the high compressive strength and low volumetric change after heating and reaction condition, promoting Vetterite formation, enhance the fire resistance through the physical interlocking of the reaction products. X-ray nanoimaging confirmed that the differences in the interlocking structure of reaction products influence the strength change upon heating. And results suggest that the incorporating a relatively small proportion of OPC improves the reactivity of CSC, previously known for its low reactivity and high activation energy, while enhancing the both CO2 sequestration and the fire resistance performance. So thank you very much for your attention, and I now be very happy to answer any question you may have about my research or presentation. Thank you for listening.